always on Google, it happens for me.
Or if you could share that on a Google Drive or something in Gmail.
Yeah, but it is 79 MB.
Doesn't matter. It will save it as, send it as a Google Drive file. There is no problem.
So anyway, I'm just saving it as PDF first in case.
Okay.
Okay, I will share the PDF also. So in case, anyway, I don't want to hold you up, Professor Sheshu. You can start anytime you want, I think.
Tejas, you may.
Yes, sir. Sure, sir. Yeah, thank you very much, sir. And thank you very much for joining us on this afternoon. Good afternoon. Today, a very warm welcome to SAMVAAD. Today, we have a distinguished INAE fellow, Professor Pradeep Mujumdar. Professor Pradeep Mujumdar is currently serving as a professor in Department of Civil Engineering, Indian Institute of Science, Bangalore, and as a chairman in the Interdisciplinary Center for Water Research in IISc. In addition, Professor Mujumdar is also an associate faculty in the Center for Earth Sciences at IISc, Bangalore. Professor Mujumdar graduated from KREC, or the present NIT Surathkal, in 1981 and subsequently obtained his master's in 1980 from IIT Kharagpur and a PhD from Indian Institute of Science, Bangalore in 1989. Prior to joining IISc as a faculty in June 1992, Professor Mujumdar served as a faculty in IIT Bombay from 1989 to 1992. His area of specialization are water resources with a focus on climate change, impacts on water resources, statistical downscaling of GCM outputs, urban flooding, planning and operation of large-scale water resource system, and uncertainty modeling. His recent research contributions include detection and attribution of hydrological change, development of downscaling models, and quantification and reduction of uncertainty in climate change impact assessment. He has served as the chairman of Water Resource Management section of the International Association for Hydro Environment Engineering and Research, and as a reviewer for the Assessment Report 5 of the Intergovernmental Panel on Climate Change. Professor Mujumdar is a recipient of various awards and fellowships. These include the Alexander von Humboldt Medal of the European Geosciences Union, the CSIR Indian National Hydrology Lecture Award, the Distinguished Visiting Fellowship of the Royal Academy of Engineering UK, and J.C. Bose National Fellowship. He is also a Fellow of Indian National Academy of Engineering, Fellow of Indian Academy of Sciences, and a Fellow of Indian National Science Academy, INSA. Please join me in welcoming Professor Pradeep Mujumdar for SAMVAAD. Sir, it's our pleasure to have you on SAMVAAD. Before I hand over to Professor Pradeep Mujumdar, I have a small request to the audience. Please type your questions in the Q&A box in the bottom right side of the screen. Sir, over to you. Welcome and thank you again for accepting our invitation.
Thank you very much for that warm welcome. I hope you can hear me clearly.
Sir. Yes, sir.
Yeah, okay. So it's a great privilege for me to be associated with IIT Dharwad, and very nice to deliver this seminar. So I particularly thank Professor Sheshu, Director of IIT Dharwad, and his colleagues for organizing this. And also the INAE Bangalore chapter, which is, I must acknowledge that it is the most active chapter of INAE in the country. So in this particular talk, I would just focus on floods, which are a large-scale phenomena. Perhaps earlier talks in INAE Bangalore chapter would have been restricted to smaller spatial scales. These are long time scales as well as larger spatial scales. And as we are aware and we have experienced, the floods are increasing in recent years in intensity, magnitude, as well as duration. And these are happening over several regions simultaneously and causing an enormous economic and life damage of the humans and other lives. So I'll just give some background on what has happened in the recent years. So is the slide moving, Professor Sheshu?
Yes, sir.
Yeah,
okay. We are in slide 2 now.
Okay, fine, thank you. So this is Chennai floods of 2015, and most of us would have seen, at least on the TV and the newspaper. This was a devastating event with over 400 deaths, and then about 2.3 million houses were inundated. But what is important from the hydrologic point of view is that the rainfall received on December 1st, 2015, that was the most critical period of this, was a 100-year record-breaking rainfall event. By a 100-year rainfall, I mean once in about 100 years, this kind of magnitude is expected to be equaled or exceeded. But exactly when the city was flooded, there were extremely high releases from 2 upstream reservoirs, and that aggravated the floods. So this was one very major event that happened recently. Then recent years, this Kerala floods of 2018, in fact, it recurred again 2019, again also in 2020, but in different regions. But as far as the devastating effects are concerned, the 2018 flood was highly devastating, where about 430 deaths occurred, 5.4 million people were affected, and 1.4 million people were displaced. Again here, the rainfall was about 42% higher than the normal rainfall. And as you can see, the total economic loss approximately was rupees 31,000 crores. That is a huge loss. And apart from the instantaneous loss that the floods cause, there is also a long-term effect that the citizens go through. Then just the last year, this was again a very devastating and tragic event of the Himalayan floods. We must have seen on the TV and the newspaper that there were some 2 hydropower dams being constructed there, and all the workers were trapped in tunnels like this. And you can imagine the tragedy that would have struck them. And large number of deaths took place, 70 deaths. In fact, I understand that the NTPC, which was constructing these hydropower projects there, the highest officer was involved in that construction, and he was also trapped and died in this. So this deluge wiped out 5 bridges, some of which ran 40 feet above the typical river levels, which means you can imagine the amount of water that would have come as floods to cause this kind of disruption. Then just the last year, I'm just giving 3-4 examples to drive home the point that year after year we are facing this deluge. So flooding destroyed, this is just last year, and Bangaloreans will know this. October, November 2021, there were very heavy rainfall. And this was again 100-year rainfall event, about 153 millimeters on a particular day. 18th to 19th, it was 142 millimeters. So this is important. That is recurring rainfall of high intensity, day after day after day, high intensity rainfall, they cause enormous deluge and enormous property damage and so on. So this you must be aware also. It made a big news that JNCSR, that is the Jawaharlal Nehru Center, they lost all their research material collected over 25 years and also scientific equipment worth lakhs of rupees. So this just happened about 3 months ago. Now there are 2 aspects to this now. One is what is happening in the atmosphere in terms of increasing rainfall intensities. And another is how we are managing this land use, land patterns, etc., especially in the urban areas. Have we messed up with the land use and the developmental activities that we take so that the response of this ground to this high intensity rainfall, that has deteriorated over a period of time. Also, the density of population in these cities, especially in the urban areas, those densities have increased tremendously. So we need to look at both the aspects. One is what is happening on the precipitation intensity itself. Are they increasing? And can we say that this is because of the climate change? Then we come down to the ground and then start looking at changing flood risk and vulnerability, which sections of the population and which sections of the city and the river basins are more vulnerable, and so on. Also, the response of the land itself, has it changed over a period of time because of the land use change, especially urbanization and then deforestation, etc. Has it caused increased flooding in the regions? That's the question that we need to ask. And there are scientific questions also. Can we use numerical weather prediction models coupled with hydrologic models to see whether we can forecast the future floods in especially the high intensity rainfall, combine it with hydrologic models to see whether we can forecast the floods. Now, this is the IPCC report. IPCC is Intergovernmental Panel of Climate Change. This is a body of scientists, as you must be knowing, and they have projected, the most recent report has projected that in our region, the rainfall intensities are likely to increase. So these green dots here show that they are likely to increase. However, they also address the question of whether these increases can be attributed to human contribution because of the anthropogenic interventions, etc. Are these causing? But that confidence is low. However, what is of importance to us is that the intensities are likely to increase in future. So already we are seeing the evidence of this. So in this talk now, I will consider two scales. One is urban scales, what is happening on the city level. Another is the river basin scale, large river basins, how the floods are increasing and how we handle these floods. So urban floods, most of us are aware, city after city, year after year, we see these kind of situations. In fact, in a lighter vein, earlier, people used to say earlier owning a car was a luxury. Now, people say that you need to own a boat because every monsoon you have these kind of situations. And then this is a very common scenario in cities like Bangalore, Mumbai, Hyderabad, and so on. So year after year, the intensities are increasing as well as the floods on the ground are increasing. So the question now is, because of urban development, what have we done to the hydrology itself? If you just look at this graph and these two figures here, same intensity of precipitation happening on a pristine land use like this will produce a smoother response from the ground. So this is flow versus time. If we look at, this will be a smoother graph, whereas anything that falls here on the urban area immediately starts falling on the surface, running off on the surface, and therefore the peak will be much higher compared to non-urban areas. The time to peak will be much, much smaller, and the total runoff that is generated for the same intensity of rainfall, same duration of the rainfall, will be much higher in the urban areas. So this poses a major challenge. Now, why these intensities are likely to increase? There are several reasons, but one of the reasons is also the urban heat island effect. That is, we use materials of construction, also waste energy, for example, air conditioner, cooling systems, air pollution, etc. All of these together contribute to urban heat island. For example, this is an urban area and the surrounding non-urban area here. It has been shown that because of the urban heat island effect, the precipitation intensity is likely to increase as much as about 100%, just downstream of this kind of a pocket. But now recent studies also show that it is not just the downstream, but also the surrounding areas also receive an enormous increase in the intensities, have evidenced an enormous increase in the intensities. So for Bangalore city then, we have done some work. So in the next part, I will show what we have done to address this kind of a problem. Now, we started this work thanks to IITDh-Water, that is Information Technology Research Academy. This is a MIT body. We took this project up about 6-7 years ago. And we want to address the flooding issue, especially in urban areas, from end to end. That means starting with the atmospheric processes down to implementation on the ground, provide an understanding of these floods, as well as try to see whether we can generate solutions. So we look at how historically this region has behaved. So we do the historical analysis on the intensities. We also look at the climate change impacts on how these intensities are likely to increase in future, complete with the uncertainties associated with it. Then we bring down to the ground, we developed overland flow modeling. And then with that, we also check whether the stormwater drains and other flood control measures that are existing in the city are adequate. And that's what we call as adequacy analysis. In the process, we also developed water level sensors. Typically we have in all the cities, we have rain gauges, but hardly any city has water level sensors. So imagine that we have a large number of water level sensors all across the city, and continuously they are sending you the data. And with that data, you should be able to assess what kind of flooding is likely to happen now or the next 1 year, the next 1 hour, 2 hours, etc., so that you can take preventive actions, adaptive actions. Of course, the side products of all of this would be we generate flood hazard maps, characterization, management, etc. So these are really long-term issues, long-term planning issues. What has happened over a long period of time and what is likely to happen over a long period of time in the future. We also identify what are called as the localized climate zones, LCZs. For example, concentration of tall buildings, concentration of medium-sized buildings, and so on, and also gardens, water bodies, etc. So these are localized climate zones. And we do a great deal of value addition by bringing in LIDAR survey, which provides us, LIDAR is light detection and ranging. It provides us with very high terrain information, high resolution terrain information of the order of 4.2 meters and so on. Anyway, this outreach and communication systems, I'll come to slightly later why it is important, because the capacity is simply lacking in the country to address all these issues, especially at the implementation level. Then we start looking at the real-time forecast. What I showed earlier was a long-term issue, and now we start looking at the real-time forecast where, as I said, we install, right now we have installed 26 sensors, water level sensors in the city, along with 100 rain gauge centers, thanks to KSNDMC. There is a Karnataka State Natural Disaster Management Center. Now, this sensor infrastructure, along with high resolution data on digital elevation models, land use, land cover, stormwater drainage maps, flood vulnerability area, all of this, we put it into urban flood model. In the process, we are also in the currently developing rainfall forecast models using the WRF model, that is the weather research forecasting model. But right now, we have linked the SAC Ahmedabad forecast into our hydrologic models. So we do all of this and then develop hydrologic models, which has all of this information built in. So we do calibration validation with several events and then set up these models so that given the forecast, we should be able to tell where the flooding is likely to happen, to what extent. Now, all of this knowledge now we have converted into a mobile app. Even as I speak, you can just look up the Google Play and look at Bangalore Mega Sandesha. This mobile app provides at any given point what kind of rainfall is likely to happen, is happening. In fact, it is a near real-time information that it provides. Now we are trying to integrate the forecast also into this app so that we provide not only the rainfall forecast, but combined with our hydrologic model running at different scales in the city, we should be able to provide the flood information also. Then all of these are slightly minor level details. I'll come to that if time permits. Now, this was followed up with a DST project. Initially, we started with the MIT project, and now this is a DST project, which we completed just recently. That's last December we have completed. Then we have taken it up with the National Supercomputing Mission. Now, it is also important for us to realize that especially in urban areas, the high intensity precipitation has a significant variation across space. For example, if you are looking at Dharwad itself is a very small town, but even then, even in such small towns, high intensity rainfall happening in one place, for example, the Valmi campus, you just go about 5 kilometers away, the intensity will be much, much smaller. And in fact, it may not be raining also. So it is important for us to assess the maps of this high intensity rainfall, the spatial maps. What this shows is a 10-year return period map, which means that once in about 10 years, these kind of intensities can be experienced. This is in millimeters over a day. Why this is important? Let us say that you are planning for some critical infrastructure here, maybe nuclear plant or some such thing. You cannot go with the average intensities that is happening all across the city. The intensities at this location may be much smaller compared to intensities at this location, and therefore, depending on the criticality of that particular infrastructure, you need to use the correct intensities. We then looked at the temperature, what is happening to the temperature. There is some question or debate about why this was decreasing here. We'll not come to that right now. But from 1940s continuously, the temperatures are increasing. And this slope is quite high, as you can see. We have gone up to about 2012, but recently we have also collected data up to about 2018. The trends are continuously increasing, as indeed in most of the cities in the country and elsewhere. The temperatures are continuously known to be increasing. But then we also start looking at the rainfall intensities themselves. You look at this was the farthest period in history, that is 69 to 86. If you look at these intensities, these were much smaller compared to what is happening in the most recent period. Now, these are the durations that are of importance. In fact, in urban areas, we go to durations of 30 minutes, 15 minutes, and so on. This does not mean that the rainfall is happening only for that particular duration. It is that critical duration which causes the flooding in the city. So, in the urban areas, as I showed, the time to peak is much faster, and therefore we consider events of 30 minutes duration, 15 minutes duration, and so on. So historically, we see that the intensities are continuously increasing. These are the rainfall intensities. But then we also ask the question, how are these intensities likely to increase in future in response to climate change? Now, this is a very tricky question and also burdened with a lot of uncertainty because the climate models work on large spatial coarse scales, large spatial resolution. That is the coarse scales, and also on the time scales, large time scales. So we adopt what are called as the downscaling techniques. Now, this is from a Japanese model that I'm showing. The Japanese have, through these kind of modeling approaches, they bring it down almost to not only the city scale, but also to the block scale by judiciously combining dynamic downscaling with statistical downscaling. So up to a certain point, you come with the statistical downscaling and then use your WRF kind of models and bring it down to very small scales, including they say that they can bring it up to city blocks, building scale and so on. So this is a downscaling that we adopt. But when we adopt downscaling, there is a model uncertainty because several GCMs and several RCPs, these are the scenarios, representative concentration pathways. Now, each GCM and scenario combination provides us with a different projection altogether. And therefore, there is an uncertainty associated with what we are projecting for the urban areas. And this uncertainty we address through our hydrologic scale invariance theorem, where we are relating not the entire time series, but we are relating the extreme values, the moments of the extreme values. So you imagine that we have an extreme value distribution, and then we relate the moment. For example, lambda t can be 15 minutes and t can be 24 hours. So knowing what is likely to happen at 24 hours, we should be able to relate what is likely to happen at 15 minutes in as far as the extreme values are concerned. We are not worried about the entire time series reproduction. So when we do all of this, and we take about 85 simulations so that uncertainty can be addressed correctly. And this is the reliability ensemble averaging uncertainty that we do. As you can see, as I have been saying, the time scales are of this order. For example, half an hour, 15 minutes, these are very important. And at these scales, the rainfall intensity is likely to increase almost 100%. And these are the ones that actually cause the floods. And the observed data is here with respect to the observed data. As the time duration increases, there is not too much of uncertainty, nor is there a significant increase. But these are the scales that are of importance to us. So this is what we provide for climate change impacts. We pick up all these intensities and bring it down to the ground. And as I said, luckily we have high resolution data available to us in the Bangalore city, thanks to KSNDMC, BDA, and other organizations, including BBMP. We use all of this high resolution data and then convert these, these are called as the Saint Venant's equations. Those who are working with hydrology will know. Simply continuity and momentum equation. We convert it into numerical schemes and then develop high resolution, use the high resolution terrain and land use maps and provide solutions. So the solutions will provide for a given intensity of rainfall, how this ground is likely to respond in time as well as in space. So we should be able to tell for a given intensity of rainfall, what kind of flooding is likely to happen. That's the idea there. So as I said, we collect all of this data. So Bangalore, thanks to KSNDMC, we have 100 telemetric rain gauge data available. And although this data is small, let's say only about the last 9 to 10 years we have been able to get this data. But what we have also done is we have used the larger time series data from IMD. There are 2 IMD stations also, which have about 60, 70 years of data. We use that data and see whether we can extend this data available here for smaller duration. And that we have done using some AI techniques. Then we extend the data in most of these. We were not able to extend it for all the stations, but in most of these, I think about 60% of these stations we were able to extend. So we get an enormous amount of data, especially spread data on rainfall. We also have the stormwater drainage as well as the small water bodies that are existing, lakes and water bodies, etc. So we take all of this and as I said, we build water level sensors. In fact, this was done through our METI project. We actually developed water level sensors through our collaboration with CDAC, Trivandrum, and we put these at very critical locations so that the information that is available from these locations, the spread of these sensors, will be useful in assessing what kind of flooding is happening in real time and also calibrating our models, hydrologic models. So these are some of the locations. So this is for one valley I'm showing here. And this valley, say for example, this is a Hulimau Kere outlet. There is a small water body here. And that outlet we have put the water level sensor as I showed here. So this water level sensor does not actually touch the water level. It will be sitting somewhere above and then sensing for every 15 seconds. In fact, we can calibrate, but we capture the data every 2 minutes. Every 2 minutes we capture and then aggregate over 15 minutes. So this kind of information will be useful when we look at the flooding situation. Then we also use the LIDAR data. In LIDAR, we get the terrain information at resolutions of 0.2 meters by 0.2 meters, which is extremely important in urban areas. In river basin scales, etc., this kind of resolution is not important. We may use about 30 meters also in river basin scales, but in urban areas, because of the heterogeneities and because of the very dense development that has happened, it is important that we capture the data at very high resolution. And we use this LIDAR data essentially to showcase to the government that if we have this kind of data, we should be able to do a thorough job of predicting the floods. And this is the kind of data, as I said, we get 10-meter resolution DEM. DEM is digital elevation maps, which provides us with the elevation at every 10 meters grid size. So this is a high resolution map that we have got from NRSC. Then we have the LULC map, land use land cover map. This is obtained from BDA. This is also a very high resolution land use land cover map. And this keeps on updating. BDA updates every once 5 years or something. And we capture this kind of data. Then we also have the stormwater and lakes, as I showed earlier, both from BBMP as well as RRSC. Using all of this, then we set up our hydrologic models and show. On this scale, it is very difficult for you to appreciate, but what it shows is, you look at this small dot that you are seeing here. After the rain starts, this starts overflowing. This drain or valley or nalla starts overflowing. And then this overflow keeps increasing. Within about 50-60 minutes, all of this area gets flooded. Now, this scale, you may be finding it difficult to appreciate, but this may mean that an area of about 5 to 6 square kilometers is completely flooded. Now that we do with different levels of intensities. And we also show through LID measures, these are the low impact development measures. There are several measures that we can take. For example, infiltration trenches and rain gardens we combine. We identify locations where such low impact development measures can be put so that you can reduce the flooding. So we show about 29% of reduction in aerial extent of the floods can be reduced. Similarly, the depth of flooding can be reduced. And we can play around with this, identify locations. This is for a particular valley I am showing. We identify locations where there is space available and implement these very small scale measures. For example, you may have permeable pavements as well as rain gardens together. If you do that, then the intensity as well as the extent of rainfall can be reduced significantly. Then, as I said, we are also developing WRF model, weather research forecasting model. We started with 2793 kilometers. Now we are going 93 and 1 kilometer resolution, and we pick up this model data from GFS. That is a boundary condition from GFS, and we compared this with the SAC Ahmedabad product. SAC Ahmedabad produces a forecast for Bangalore city, and we use that. And we are trying to improve upon that because the SAC Ahmedabad model runs for the entire country. And then we just clipped for Bangalore city. So now we are developing it only for Bangalore city. And we see that some of these events that have happened recently, we were able to reasonably well predict those. For example, September 8 to 9, 2020. And then we also integrate these forecasts with our hydrologic model. This is a HECRAS 2D model, and then show how we are able to reproduce the flooding that actually happened if we use the WRF model outputs. Now, this has an implication that once we are successful in reproducing what has happened, we should be able to forecast using the same forecasting model as well as the hydrologic model. This we do at several valleys. All of this now we have combined into a mobile app, as I said. But when we started it in the ITRA project, we went up to sending WhatsApp messages. So we get the rainfall forecast. Initially, we got from SAC Ahmedabad. Now we are also developing, combine it with the hydrologic model, and this runs on the KSNDMC server. I must acknowledge that most of this work we were able to do successfully, mainly because of our collaboration with KSNDMC. And then this server transmits it to alert decision-making system where all these maps, etc., are built in. And then it sends what it used to send WhatsApp messages. Now also WhatsApp messages are there, but we have joined all of these. We have combined all of these into Bangalore Megha Sandesha application. So you can download this, and then during rainy period especially, many people have given us very nice, very good feedback. But there is also some limitation here. As of now, we are getting this information almost with a 15-minute lag, and we are trying to enhance the efficiency of that so that we can provide almost on a real-time basis. So this is about what we do on the science scale. Now let us look at what we do on the ground. For example, if you have pavements like this, which are almost like blotting paper, as the water flows, so does it get absorbed. So like this, suppose we have material like this, and then you build your pavements as well as parking lots and so on, then whatever the flooding that is happening can be pushed inside the ground. Provided the geology is favorable. So we need to identify where the geology is favorable and identify locations where you can put such material so that it can be absorbed. So these are some of the advantages and disadvantages. I won't go into those details. But what we have done in the process is that we experimented within IISc campus as well as in KSNDMC. We took help from our structures lab, and we actually developed this material. Porous pavement material, because porous pavement by itself is not a new material, but we wanted to overcome all the disadvantages that it has. Namely, this gets dusted and all these dust particles, etc., get accumulated. So once in a while, it needs to be cleaned and so on. And also, this is not a load-bearing pavement. You cannot pass your moving trucks and things like that. So it has to be used essentially for pedestrians as well as parking lots where there is not too much of a movement. But even with that, the efficiency is quite large. We have done a large number of experiments, and we have shown that if we put this at several locations in the city, you can actually reduce the flooding. Then we also looked at the groundwater recharge potential. As I said, if you can put these at locations where there is a huge potential for recharge, because the flooding is happening at a very rapid pace, and the way or the pace at which we can push it into the ground is much, much smaller. So we need to essentially identify where we can put such pavements and other measures of infiltration so that water can be pushed rapidly inside. As we can imagine, in the central portion, the recharge potential is very poor because there is a huge leakage of water, etc. So in developed areas in general, the recharge potential will be small. But just outside the main city, outside the central city area, we have huge potential for water recharge. We are talking to the BBMP now. In fact, in the next project, we are taking this forward. Then there is another technological intervention that we are talking about. These water boards, similar to the robos, they can actually move inside our stormwater drainage and send signals of where the blockage is and what kind of blockage is and so on, what kind of water levels are increasing and so on. Now, this is important because unfortunately in countries like ours, when the flooding happens, it is not just the flood water that flows. It is the people and livestock that actually flow into the, they get stuck into the stormwater, and many people die during that period. So when we were talking to the fire department, they said that this kind of technology will be extremely useful for them in identifying actually the bodies so that they can save those people. Now, this is one thing that we are experimenting in the next project, which is through NSM, that is a National Supercomputing Mission. Now, I'll go slightly into a higher scale where we are talking about the river floods. Getting flooded, and that is what we are trying to do. Now, urban scale, on the river basin scale, again, as you are aware, the Himalayan rivers get flooded very often. So we have taken here Alaknanda and Bhagirathi. This is Upper Ganga basin that I am showing. For example, you have Tehri here, and then Joshimath is here, 3, and Rudraprayag is here, and so on. Rishikesh is here, number 6, Rishikesh. So this will give you some idea. And these areas are getting flooded year after year. So we see that just looking at the historical part, there is a Rudraprayag, which is here, number 4. Here the intensities are shown to be increasing. Now I'm talking about the flows now. I'm not just talking about the rainfall. We actually had the flows here, and we did the extreme value analysis and showed that post 1995, these intensities are continuously increasing. And we are looking at 10-year return period, 100-year return period, and so on. With this knowledge, then, we must be able to see what is likely to happen in future. Right at the beginning, I mentioned that it is incessant heavy rainfall that is important. For example, day after day after day, you may be getting 50-year return period flow, 100-year return period flow, and so on. It is not as if 100-year return period flow or rainfall happens today, and then we have a lull. Most of these critical events have happened because consecutive days, for example, 4 consecutive days, and September 2 to September 6 in Kashmir floods, similarly July, August, Kerala floods, all of these are happening on consecutive days of extremely heavy rainfall. So capturing that is important. So what we did is that for Uttarakhand 2013 floods, which was also a devastating event, we looked at that particular location, we looked at how it is behaving in terms of clustering of these extreme rainfall. That is 4 days continuous rainfall above a particular threshold. And how to fix this threshold, etc., is a bigger story. We will not worry about that. So if we fix a particular threshold and see how many such clusters are there which have exceeded 4 days, exceeded that threshold on consecutive 4 days. When we do that, there is an increase in the probabilities of extreme rainfall spells for both these sites. So we took these 2 sites, namely Rudraprayag and Uttarkashi. And for both these, we observed that this clustering of high intensity rainfall has increased. Now, this has implication on future developments when we are looking into the future. Now, all of this has a premise that history provides a valuable clue to the future. So we base our premise on the historical data and then start looking into the future. But now the future is not likely to be similar to the past. So we ask the question, what happens to the concept of return period itself? By return period, I mean once in about so many years, such kind of intensity is likely to be equaled or exceeded. That's the return period. Now that return period, traditionally we used to estimate based on the historical data. But as I said, the history is no longer providing a valuable clue to the future. So we need to do something else. And then that is where we build the non-stationarity concept. Unfortunately for Indian river systems, we did not have the data. So we looked at the Columbia River and asked the question, whether and when in future, the historically assessed return levels are likely to be exceeded. So that's the question that we ask. So you look at this color here. This is a stationary return level for 75-year return level. And these are the non-stationary return levels. That means that we build non-stationary models where the return levels are continuously increasing. Sometime in future, these are likely to be significantly different from what has been estimated with the historical data. And we say that whatever you estimated using the historical data is valid until about 2027 here, and for 100-year return level 2065. And beyond that, your hydraulic structures, dams, spillways, etc. will not stand the designs that you have made based on the historical data. And this we are currently doing for Indian cities, Indian river basins also. The last part that I would like to discuss, last but one in fact, is exactly these locations which are getting highly flooded. Unfortunately, we do not have data because these are all high elevation data. There are high elevation regions and there are not too many gauges available. Then we ask the question, can we use these globally available data sets and see whether using our WRF kind of models as well as hydrologic models, can we reproduce what has happened in the past? So that's the question here, model reconstruction of Uttarakhand floods. So we had discharge data at certain locations, but not significant rainfall data. So we use all the available climate data, set up WRF model, high resolution WRF model, and then combine it with the hydrologic model to see whether we can reproduce what has happened on the ground. So there are lots of methodological details here, we'll not worry about it. What we conclude then is that when we combine WRF model with WIC model, this is a hydrologic model for flow simulation, we have been able to reproduce out of 5, we were able to reproduce 3 of them with respect to the highest flows. And we are trying to improve upon these at river basin scales. If we succeed, the idea there is that even if we do not have ground level data on rainfall and stream flow, etc., at critical locations, we can fall recourse to globally available data, set up our models, calibrate and validate our models, and able to reproduce and therefore forecast these kind of models. Now, the last part is on all these infrastructure that we have. For example, I'm showing the Hirakud Dam. The flood intensities are known to be increasing on most of the rivers. But these reservoirs are operated essentially for hydropower, irrigation, etc., where the focus is to build up as much storage as possible. And therefore, we start looking at how these need to be operated, given that there is an uncertainty associated with the flood magnitudes as well as discharges. So we develop optimization models combined with uncertainty, combined with the reliability of hydropower generation, so that we do not sacrifice on the hydropower generation, but we look at how this reservoir needs to be operated during the flood period. So July to October, how it needs to be operated. These are the water levels. So we prescribe that instead of operating as per your current rule curve, you operate it in certain manner so that you are not sacrificing on the hydropower generation, yet at the same time you are able to prevent the floods or mitigate the floods. This is the last part. which is connected with Kerala floods of 2018. We did a significant study on this because the CAG, that's the Controller and Auditor General, asked us to carry out this for 2018. Essentially, we looked at all of these dams here. There is a Mullaperiyar is here, Idukki is here, and then Idumalayar is here, and this side is the ocean. So, and this is the Periyar Basin. In 2018, this Periyar Basin received unprecedented rainfall, almost 105-year rainfall and so on. Now, the question was whether the flow that is generated in this free basin itself was very high, or dams also contributed to this. And this became a slightly controversial question. And we addressed it very rigorously and showed that, with the available rule curve, by rule curve, I mean this, something like this. With the available rule curve, they could not have done anything better. So we have suggested that the rule curves themselves should be revised. And with all of this, then we should be able to simulate like this. So what we do is that we simulate various conditions. For example, the flooding will also be affected by tidal levels. So we put these as the boundary conditions, and then you start looking at this, how the water level is likely to increase. As this flooding level, as this tidal level increases, obviously there is no gravity flow possible, and therefore the water flows back into this and causes enormous damage. At this scale, again, it may appear very trivial, but these are different towns that I'm showing here. So several of these towns get flooded with this kind of intensity. And we can play around with these with different intensities to show how quickly and how much of flooding will happen, both in terms of the intensity as well as in terms of the magnitude and duration. So this is about what science can do in terms of providing an understanding of the flooding situation. So in summary then, we know that the intensities of rainfall are known to be increasing across different space-time scales, and we will be concerned about urban scales as well as the river basin scales. For example, the Kosi River floods has its own story, Kerala floods has its own stories, Uttarakhand floods has its own stories, and so on. So we must be able to understand what is likely to happen to different river basins as well as different cities. Bangalore may behave similar to Hyderabad, but Bangalore will not behave similar to Chennai or Mumbai. So there are coastal cities. Coastal cities have their own problems. Similarly, the density of the population and the density of urbanization, that itself causes its own problem. So city after city, we need to address these problems. Right now, what we are doing is through NSM, that is a National Supercomputing Mission, we are putting all of these models. This is with collaboration with CDAC, Pune. They are the lead partners. We are putting all of this model framework along with the data on the supercomputing platform, so that any city wants to use it, any researcher wants to use it for their city, this can be used. So I stop here, but during discussion, perhaps we can add more value. So I again thank Professor Sheshu and his team for this opportunity. It has been wonderful for me to talk to you. Thank you very much.
Yeah, thank you very much, sir, for a very nice, incisive talk. We have some questions in the chat box, which I would like to read out, sir.
Yeah.
So firstly, the question goes is, can we design and build covered and underground lined fairly big sized ponds, especially in urban area, which can collect and keep the rainwater? This will release the land at the top of the pond for housing or agriculture after the pond is constructed. Something similar to hanging gardens in Malabar Hill area in Mumbai, where there's a big tank on top on which there is a park for people to relax.
Yes, thank you very much for this question. In fact, this is a very relevant point, because the urbanization has grown in such a way that many engineering solutions are possible, but they will require huge interventions. So the idea that you suggested is possible, except that what happens is, if we are going below the ground, then the levels that we need to maintain, for example, finally it has to drain out somewhere, and those levels will dictate how much we can explore into the ground. But I'll give you one example of large-scale engineering intervention. So the urban floods especially, you look at Bombay or even Bangalore and so on, where the density of growth is very high. So any solution that you think about on the surface is very difficult now. So anything that takes up land is extremely difficult. Now, what I think Kuala Lumpur has done is that the tunnels that are used for transport, road tunnels, during the heavy flood situations, they close it for traffic, divert all these floodwaters into the tunnel. So tunnel actually becomes as a storage point, temporary storage point, huge amount of storage on the surface. And then once the flooding recedes, then the traffic is made open. So similar to that, now there is a talk about underground drainage itself. But underground drainage again has its limitation because finally it has to drain into another water body somewhere. And those slopes will be deciding on how much of drainage you can use. Of course, what you said is absolutely correct, that we must be able to explore, and these large engineering solutions are always possible. But we are also advocating non-structural measures, low impact development, so that the intensity of the flood can be reduced. We cannot do anything with the rainfall intensities, but once it comes on the ground, we should be able to do several things so that the impact of the flooding can be reduced.
Sure, sir. Sure. Thank you, sir. Next question, mostly it's more related to Bangalore city. Bangalore city depleted its lakes. Is it possible to advise on critical size, critical location of artificially developed water bodies to mitigate the effect of flash floods?
Exactly. Because of lack of time, I did not show this. What we also do is that we show, okay, I don't think I have that slide, but let me explain that. So through our models and all, we show how much of buffer storage can be given if you maintain the lakes correctly. So what we have done is that we show, for example, there are some lakes, and we have actually used the remote sensing data. We have shown how the lakes have depleted in the city, because of which how the flooding has increased. Now we use this information and knowledge to show where you can put small water bodies. That's what I meant by low impact development. Even large complexes, housing complexes, etc., the gated communities that are coming up, even there, we must be able to have small water bodies. In IISc campus, we have done that. We have small water bodies. We transfer all the rainwater into that small water body. It also recharges, as well as it provides a good ecological, space for birds and things like that. So it has multiple advantages. So lakes do, form a buffer for floods, and they are in fact insurance against the floods.
Sure. Thank you, sir. Another question again coming related to Bangalore itself. Water passages in the city get choked with debris, plastic waste, etc. Although BBMP might be doing cleanup and requires manpower and mechanized equipment, can we have a techno-social economic solution? Is there a ways to solve it, sir?
Yeah. So again, because of lack of time, I did not show that. What I said is exactly when the stormwater drains are supposed to perform at their best efficiency, they get choked because there is a huge solid waste. As Indians, we are used to using any space that is available for our solid waste disposal. So what happens is during non-monsoon and non-rainy period, these drains are all empty. Mostly they are empty, although they also carry sewage now. So we use them as solid waste dumping grounds, and therefore they get choked. So many of the major drains, unfortunately, we have all the maps. Major drains get choked exactly when they are supposed to be absolutely free of all of this. Now, after every monsoon, and I'm not blaming any government agency here, but after every monsoon, people are sensitized that we must clean these up, etc. So they clean it up after monsoons. But what is necessary is before monsoon, all of these should be free of solid waste and so on. But the modeling exercise will help in identifying where the choking happens, as well as what is the effect of choking on the overall flooding scenario.
Sure, sir. Sure. Another next question, sir. It's more related to Mumbai. In Mumbai, at least from 1963 onwards, every monsoon Mumbai gets flooded due to backflow from sea during the high tide time. So the question is, how do you go about addressing these kind of issues?
Yeah. So for Mumbai also, IIT Bombay, my two students are there, Subankar and Subimal. They have done for Mumbai as well as Chennai. Now, this is a problem with any coastal city, even Chennai we have seen. With respect to the tidal levels, the gravity flow will be affected, and therefore there will be backwater flow, because of which the flooding will happen, and flooding will happen very quickly. And in cities like Mumbai, you do not have scope to do anything on the surface, which will take larger amount of larger land area and so on. So the question is, if you want to go with engineering solutions, there are many solutions. For example, hold back the water using certain pumping and so on, localized pumping, and then use your available tanks and so on. And like I said, in Kuala Lumpur case, on that, use that as a solution, and then you use them as a temporary storage. So coastal cities have typical problems, and engineering solutions are possible. Large-scale engineering solutions are possible, but they'll be extremely expensive, and in the long run, they may cause nuisance.
Sure, sir. Thank you, sir. Sir, question slightly going away from the urban. Dry regions like originally known dry regions like Kopla and Raichur are now seem to experience a lot of floods. How is this change accounted for, sir?
Yeah. So, I'll just give some background if there is time.
Yes, sir. We do.
So we have seen all across India, the distribution of the rainfall is changing. While your seasonal rainfall, in one simple term, I'll tell you, your seasonal rainfall may have remained the same. If you look at last 30, 40 years or even more, the seasonal rainfall may not show any trend, but the distribution of the rainfall within the season has changed significantly all across the country. And this is what is causing areas, this is spatial as well as temporal distribution I'm talking about. So spatially also the distribution is changing. Exactly where there was absolutely no rainfall or dry regions, including regions in Rajasthan, etc., where they used to get very scanty rainfall, they are getting flooded now, many of these cities. So this is happening all across. Now, is it because of climate change? That's a typical scientific question that is to be addressed. Now, the science has still not grown or matured enough to say pinpointedly that what happened this year is because of climate change, or what happened last year is because of climate change. So the science is still growing in that direction. However, year after year, space after space, seeing these unusual events, we generally speculate that something is happening on larger scales, and that is what is causing this problem. But that it is happening is what is important, and we need to find solutions to those.
Sure, sir. Thank you, sir. Maybe next question is more related to your research, sir, from your group. For doing the impactful work that you and your group has done, there is a requirement for huge amount of data. Apart from getting data from other agencies, what kind of facilities your lab has, which you think are indispensable, sir?
Which you think? Last part I did not.
Which you think are indispensable, sir?
Okay. Okay, thank you for that question. And as I said, we have been not just lucky, we have put enormous effort, because being academics, we generally shy away from interfacing with the government agencies. But this was necessary. I must also acknowledge the sponsors. Sponsors also facilitated this kind of a collaboration with the government agencies. And the government agencies also realized that, we are not simply academics here. We want to do something for the city. And therefore, the government bodies came up with a lot of data. They shared the enormous amount of data. That's one part. It is obvious that all cities will not have the access to this kind of data. In fact, we are doing this work also for Baroda city. Now we are also doing for Patna city and so on, where this kind of high resolution data is not possible. Then what we do is we fall recourse to the secondary satellite data, for example, satellite products, TRMM, etc., which provide us with rainfall data. Now, we also use the global data sets to run our WRF model. But even for that, you need ground level data. For example, building parameterization and so on will be necessary. So this kind of data can be generated quickly in the sense within our next 3 to 4 months. So if there is a will from the government agencies, or if we are able to convince the government agencies that this kind of work is needed, you cannot, if something gets flooded, you can't go there and then just put another drain and temporarily solve the problem. This has to be looked at a holistic problem. And for the holistic problem, all of this data is necessary. So you must fall recourse to the satellite data, and RRSC as well as the NRSC Hyderabad, they provide us with a lot of data, very useful data. DEM data is available for all the, all across the country. Land use, land cover data is also available all across the country. You can fall recourse to the Google Maps, Google engine. You can actually get very high resolution building maps also from the Google engines. So if you build a team which is passionate about doing this work, data will not become so much of a constraint. Yes, it is a constraint in our country. There is no doubt about it. But there are many, many ways of doing this, overcoming this. So many cities will need to, enter into this kind of work. Thank you.
Sure, sir. Thank you, sir. Next question. We have another 3-4 questions, sir, which are very interesting. What are your thoughts on using these technologies for studying the underground water situation, sir?
Yeah. So in our team, that is in our center, ICVAR, we also have a very renowned groundwater hydrologist, that is Professor Shekhar. What we are doing now is that how the groundwater responds at one level, how the groundwater responds to these high intensity events, floods. That is, floods are happening, how is the groundwater responding? Is it all happening on the surface water or on the groundwater also? So the groundwater also needs to be understood through hydrology. That is the groundwater hydrology. What kind of parameters exist and what kind of pumping is happening and so on, how it responds. So the surface water and groundwater need to be coupled. And this is what we are doing at the river basin scale. But on doing it on urban scales is very difficult. So urban scales also we are trying to do with data. That is artificial intelligence kind of models driven by data essentially. Because we have a good amount of data also on the groundwater pumping in the Bangalore city. And we also have what is happening on the surface. So there is a huge potential for addressing all these problems. As I said right at the beginning, the capacity in the country to address these problems is very limited. And therefore, we are putting some effort and time to develop training programs for not only for the government agencies, but also for the researchers, young researchers who should get excited about these problems, because these are really live problems. And there is a huge potential for useful contributions.
Sure, sir. The next question, which is very related to this, the tectonic plates are generally on move, and this may change the groundwater networks. Do we have measurements or predictions of these underground networks, sir?
Yeah, this is a nice question, and I am aware of this situation, and I acknowledge this question. But I think the earth scientists, especially I think in Roorkee as well as the Kanpur, they are looking at these, how these groundwater fractures especially change with respect to the tectonic activities. At this time, I won't be able to give any more information because this is beyond my area, but I can tell you that the earth scientists are really looking at this. And how, in fact, what we would be interested in is if they are able to show for sure that for such and such a tectonic activity, this is likely to happen, we can use that information to show how the groundwater level will respond to such events. I'm sorry that at this stage I am unable to give a more complete answer.
Sure, sir. Thank you, sir. Sir, probably now a question which is more related to our academia. Given the importance of climate change and the need to cater the requirement of trained manpower, do you think it is essential to introduce specialized courses at undergraduate level, something like we have the environment and earth science in BS program of IISc, sir? Your thoughts on this?
Yeah, so the importance of these these subjects cannot be overemphasized. And our own CAOS here, Center for Atmospheric and Oceanic Sciences, as well as the IIT Center for Climate Change, they are doing MTech program on climate science. But that is all at master's level. And I understand and appreciate, acknowledge that this has to be done, the sensitivity has to grow at the undergraduate level. So all these IITs have, and I'm sure IIT Dharwad also has, a compulsory course on environmental science or something at the first year level. And I know IIT Bombay, where 800 students sit in that course. Now, in that, we are trying to introduce these. I think there is also a module related with climate change and climate issues and so on. So it is not necessary, or it is not adequate that just the climate scientists are sensitized about this. It is necessary that all the citizens, and especially the engineering graduates, must be aware and made sensitive to these issues, because these are really live issues. By ignoring that, we are simply ignoring the elephant in the room. That's it. We can say, debate ad infinitum that all of this is a hoax and so on, but it is really happening, and it is affecting the human lives, both at the city level as well at the larger scale levels. We can no longer afford to ignore these issues.
Sure. Thank you very much, sir. I think we have answered all the questions. If there are no other questions, then we would like to thank Professor Mujumdar for a very lucid talk on the pertinent issue of urban flooding. I would also like to thank, on behalf of Team SAMVAAD, the audience who have taken time out of their busy schedule to attend the talk. SAMVAAD hosts talk regularly, and the updates of the upcoming talks are available on our website. We request you to keep a tab on our website. And thank you once again for joining. And I would like to thank Professor Mujumdar for accepting our invitation and giving a very wonderful talk. Thank you very much, sir, and good day.
Thank you very much. Bye-bye.
Thank you, sir. Thank you.
Thank you, Professor Mujumdar.